Welcome back, everybody. I'm hoping to have the exams back to you guys on Wednesday, so that you guys will have a full week along with time, like a weekend, instead of having to come straight back from the weekend, and in for the to turn in your exam redo. But looking at the calendar, just so that we're kind of keeping aware of where we're supposed to be. So we are starting up week 13. So we're supposed to be going over 4.2 today. I don't know how far we'll get, but we'll hopefully try and get through all of it. But we're in week 13, week 14, and then week 15 is the last week. And then week 16 is final. So we've got 3 weeks of class left, just 6 classes, including today, and then a final exam, which, as a reminder, the final exam is cumulative. I'll post a review for the rest of the material. It's not exactly going to be a full, all-encompassing review because it's just for the last bit of material. So please utilize old exam reviews, old exams, and all that stuff to help prepare for it. Yeah, I'll be giving you your exams graded back as long as everything goes according to plan. And management, aka my son, does not have other plans for when I'm home or whatever. I'm trying to grade something. But they should be back on Wednesday, and then they'll turn back in following Wednesday, and we'll have a great time. Okay. I'll try to make sure all the materials are posted, like the exam reviews and all solutions are posted very soon. Any questions before we get started for today? Okay. And I do have your exam redos graded, and I'll be passing those back during the break. So where we ended up with was mentioning these important, these very, very useful theorems about summations. So there's the sum of every number 1 through n ends up being exactly this, n squared plus n divided by 2. It's a true story. Gauss is apparently the one who's credited with figuring it out. If you decide to take computer science, if you're a big computer science person, one of the things that you'll learn how to do in that class is a thing called a proof by induction. Not an induction, not a induction oven or whatever those things are, but the process of induction is proving something based on what's been proven before. And it's a very, very common type of problem that you encounter in early computer science programs to try and prove something is true. So these formulas actually get proven with most of the time with induction. So the key thing that I wanted to mention about these ones is that in order for you to utilize these summations, the lower limit must be 1. Now, I wish we had more time to talk about it because there's a lot of cool stuff that you can do with summations. As we were mentioning earlier in this problem above, you can start these summations wherever you want. Nothing stopped me from making the first term a sub 3000. All that would happen is if I wanted to change it to a sub 3000, if that's what I wanted my first term to be, then it would be 2 to the 3 to the n minus 3000, 2999 times 2 times not n, I. And then I minus 2999 plus 1. So legitimately, this will end up being the same formula, but you'll be starting at a sub 3000 instead of a sub 1. So the point I want to make with that is that one of the coolest things about summations is you can re-index them. It's a process very, very common, especially in upper division mathematics, to re-index something to get it to start where you want it to. So point being is if I had done this, then I could have changed this to 3000, and this would go to 3010, or like that. And so the reason why I'm bringing that up and the reason why that's so useful to us is that these formulas, as I said, these formulas have to start with your lower bound being at 1. If you don't, the whole thing goes to kaput. The whole thing doesn't work anymore because it has to start off with that 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on and so forth. So with that in mind, yeah, did have us to do these ones, didn't I? So this is going to be some good practice with the summation materials. So instead of going through and actually computing all 9 of them, we can do this in a lot faster way. We can break this up into pieces by the properties of summations. This is the same thing as 2 times the sum from I equals 1 to 9 of I cubed minus the sum from I equals 1 to 9 of 7. By the properties of summations, I can ignore the constants, bring them up front, and then I can split apart addition and subtraction. And so in particular, this is that this first one is that first, the fourth entry or third entry? The fourth entry. So this is the same thing as 2 times from the theorem above, n times n plus 1 squared, all divided by 2 squared. So n here being 9, so this is going to be 9 times 9 plus 1 over 2 quantity squared, minus 7 times, by this one, from I equals 1 to n of a constant, it's just the constant times the number. So 9 times 7. And that ends up being 3,987 when you're all said and done. Now, that is basically pre-calculus material. I don't want to spend too much time on it. The very, very big use of it, and the thing that we would spend a lot of time on if we could, would be converting it for non-finite numbers. Notice that this one is the sum from k equals 1 to n of k squared over 3 minus 2. So we're trying to create a formula instead of being like a specific number, because the upper bound is an arbitrary unknown number. We cannot find a specific number. We have to write a formula for it. So you could break this up though. This is 1/3 times the sum from k equals 1 to n of k squared minus the sum from k equals 1 to n of 2. And I promise you there will be a reason why I'm spending time on this in just a moment. This is a useful skill in mathematics for later on, but this is also useful for us to calculate area, which we'll see soon. So the sum for k squared from k equals 1 to n, that's going to be n times n plus 1 times 2n plus 1 divided by 6. So this becomes 1/3 times n plus 1 times 2n plus 1, all divided by 6 minus 2n. Or n times 2, but that's the same thing as 2n. And we could leave it there if we want to, or we could simplify it. It all depends on the situation. And you'll see why in a little bit. But that should be sufficient for us. And why would this be useful? Now, we can find out what that sum will be for any n value, including infinity. What will it be at infinity? Will it actually be a finite number? Will it not be? That's a good question. That's what you will study a lot of in Math 182 if you decide to take it when you get to sequences and series. Does that series converge? Does that series, when you add up it infinitely, does it come to a finite number? Answer for this one will be no, it does not converge. But that's for later on. And then this one right here, this is especially useful. Remember, n is the upper bound. N is just a number. I is an index. I changes as we move along the series. I will change. When we start, I will be 1, then 2, then 3, then 4, then 5, all the way up to n. But n is a fixed number. So it can be treated like a constant. So n does not depend upon I. And as such, can be treated like a constant. So what do I mean by that? Once you written that down, I'll show you. That n does not depend upon I. So in the summations viewpoint, in that sigma just sees it as another number. It doesn't know what the number is because we haven't decided what the number is, but it is a fixed number. So it doesn't, it just says, oh, that's just like 5 or something. And so you can split this apart into 2 over n cubed times the sum from I equals 1 to n of I squared plus 1 over n times the sum from I equals 1 to n of I. Make sure you understand where that all came from. And so we now know what the formula is for I equals 1 to n of I squared. And same thing for I. This becomes 2 over n cubed times n plus 1 times 2n plus 1 over 6 minus 1 over n times n plus 1 over 2. And we can leave it like that because we're not being asked to do anything with it. But if we were asked to do something with it, we might want to FOIL it out and simplify it. But as it stands, we're fine. Any questions on that? All right. So we get on to Riemannian sums or Riemann sums. These are mainly just preliminaries for what we're going to get to. So you do not need to have these formulas memorized, nor will I test you upon them, because it's just, I'd rather spend more time on the other stuff, even though this stuff is really cool. Just, I want to spend more time on the other parts of unit 4. So delta x will equal b minus a over n, and that's going to be consistent for all of them. Delta x is the width of every rectangle. And to ensure that they all have the same formula, we're going to take the right endpoint minus the left endpoint to give us the total distance of our interval and divide it over n rectangles to make sure each rectangle has the same amount of width. So the right-hand Riemann sum, I need to remove this because I'm just going to write that here. The right-hand Riemann sum is defined as R sub n, and it equals the sum from k equals 1 to n of f of a plus delta x times k times delta x. All right. Then there's the left-hand Riemann sum. And once again, don't worry, I'll explain these in just a moment. But the left-hand Riemann sum which some textbooks don't define anything. Like I like to use the definition for it, so I'll say L sub n. So for left hand. And so here is where you might start to see some differences in textbooks. Some textbooks want these all to be the same formula, whereas others, the way I like to do it, like them to have the same at the same index. So this is the way I will write it. From k equals 1 to n of f of the quantity a plus delta x times k minus 1 times delta x. Now, you don't need to write this down, so I'm just going to write this off on the side for a moment. The way that many textbooks will write this is like this. not. They'll write it this way. The only difference is that the delta x times k minus 1 is now a delta x times k. And then instead of starting at k equals 1, we're starting at k equals 0. Now that's fine. It looks prettier. It doesn't look nearly as complicated because there's no k minus 1 on the inside. It doesn't look intense. But the problem is, for computational purposes, you have to reindex anyways. Because in order to use any of the formulas on the previous pages, they all need to start at k equals 1. So I have decided that for our class, I'm always going to start them at k equals 1. But you don't have to have these formulas memorized. I think the main reason why they would do that is just to make sure it was easy to memorize, but it ends up causing more issues in the long run. So that is why I'm not going to do that. And then the last one is the midpoint Riemann sum. Which is defined as m sub n, which is equal to k equals 1, the sum from k equals 1 to n of f of a plus delta x times 2k minus 1 over 2 times delta x. The most confusing out of the bunch, and I'll explain why once we get there. The number line. So you don't need to draw this curve, by like this line, by the way. This is just for explaining purposes. So let's go with 0, 1, 2, 3. We'll do that. And then let's look at all these formulas. Sorry, 1 second. Ooh. Come on. All right. So let's think about why the formulas are the way that they are. So the Riemann sum, what it is at the end of the day, and so to ignore this page, I put this in the middle of the summer, like in the middle of break, and I had ideas for how I wanted to fix it. The next one, what does this formula mean? I had ways in which I wanted to fix it, and I added that, but then I forgot to finish it. So I just realized that now. So please just ignore that page, but we're going to explain it right here. The right-hand Riemann endpoints. So in this case, if I'm going to do this area here, that would mean that A is equal to 3, or is 0, and B is equal to 3, right? And let's just do three rectangles. The first area should come, if I'm doing the right-hand Riemann sum, should come from this, right? So that's not A, because A is 0. So if I want to use my first endpoint to find my height, I have to do A plus a delta x. So that's my first height, and then the width is always 1 here. Then I do k equals 2, that would be A plus 2 delta x's, and that gets me my second height. And then I do the third delta x, and that moves me over to here, and I have my last one. That's how the first formula works. They're all the same. If you notice, they always have a delta x at the end. That's the width of each rectangle. The f of blah portion is the height. Now, the reason why the secondary one, the left-hand endpoint, is a k minus 1 is that when I start my summation, I want to start with a. So when I plug in k equals 1, I have 0 delta x's because it'll be delta x times 1 minus 1. It'll be 0. And that will allow me to start right at the left-hand time. Then I'll do the next one. I'll plug in k equals 2, and I have to move over 1 delta x to form my secondary rectangle. And then to form my last rectangle, so on and so forth. The hardest one to understand is the midpoint. Why is the formula 2k minus 1 over 2 for that, like right after that delta x? Why is that the case? So let's look at this. The midpoint of this one would be 1/2. The midpoint here would be 3/2. The midpoint here would be 5/2. So what it appears like it's doing is it's it's always over 1/2. And then it's increasing by an odd number each time. 2k minus 1 will always be an odd number. And so, I mean, you could start it at, like, some people will write 2k plus 1 over 2, but then they have to start k equals 0. So that's the problem. So what this effectively does is make sure that we only go over, the first time we only go over 1/2 of a distance, then we increase it by we increase the k by one more value, and that makes us go one more over now, but it's really technically 1, 2, 3 halves to get us here and here and here. So that's how it works. But nifty, not super useful nowadays. It was very, very useful back in the day. But once Newton's advisor figured the next part out, that's when this just became a thing of the past. So, but like true mathematicians, we have to go through and see it from the other side. I'm going to skip these ones because it's not going to be super useful, and I'm not going to ask you to do these types of things. So we're just going to omit for now. Omit. Fine. So this is the whole point. This is how mathematicians originally figured out the area of those shapes. So find the area under the curve f of x equals x squared plus 2 on the intervals 0 to 3. So on the side here, I'm going to draw a picture. So we're using the interval from 0 to 3. So that means we're talking about the right half of the plane. The XY grid, we're only talking about the right half because we're going from 0 to 3, from x equals 0 to x equals 3. So we don't need to concern ourselves with anything to the left. And the reason why I've only drawn the first quadrant is that my curve, f of x, is x squared plus 2. That's a parabola that's been shifted up 2 units. It's the U shape shifted up 2 units. So I don't need to worry about the bottom half. That is why I'm only working with the top right corner, the upper right corner of the graph, or the XY plane. Here's 3, and we're being asked to find the area of this region. So we're going to find it for n right-hand Riemann sums. We're going to find the nth Riemann sum. Not a specific number. We're going to find it for a general n. So in the formula, we need, so this means right here, this means that a is equal to 0 and b is equal to 3, which means that delta x will be 3 minus 0 divided by n, or 3 over n. So if we were doing 3 rectangles, we do a rectangle at 1, a rectangle at 2, and a rectangle at 3. Maybe doing a rectangle right here, and then calling it good. But we're going to do this for an arbitrary number of rectangles. So R sub n, by definition, is the sum from k equals 1 to n of f of a plus delta x times k times delta x. That's the definition. So let's plug in all the things that we know. We know what a is. We computed delta x. K is the index, so there's nothing to do there. And we already know what delta x is. So we have everything except like that we need. So this becomes the sum from k equals 1 to n of f of 0 plus 3 over n times k times 3 over n. Just by definition. 0, delta x is 3 over n, k is just k, it's the index, and then delta x we just rewrote. So this right here, that is f of 3k over n. F of the quantity 3k over n. Yes, it looks weird, but 3k over n, it's a function. It's a function. Or f is a function, so we can plug in whatever we want. It doesn't matter if it's an actual number or a bunch of variables. It's okay for us to plug in 3k over n into f. It's just going to be a little weird. But f of 3k over n, by definition, because f of x is equal to x squared plus 2, this is 3k over n quantity squared plus 2, which is 9k squared divided by n squared plus 2. Yes, that's so excellent question. So because f of x is equal to x squared plus 2, I'm going to plug in 3k in for x. 3k over n in for x, and that's why the formula is now. So this is going to tell us, is that okay? Excellent question. So what are we doing right now? Let's really think about that for a second. I'm computing f of 3k over n because that will give me the height of any right-handed Riemann sum rectangle for any k value. With an arbitrary number of rectangles. So I'm computing that, and now I've got it. Now there's no more functions in this. This will now purely be the sum from k equals 1 to n of 9k squared over n squared plus 2 times 3 over n. The reason why I really like this section, by the way, is this is really what mathematicians, this is kind of a great example of what mathematicians love to do. They created this formula and then said, well, what happens when I do this? Let's just see where this goes. And so the inside of this summation is just like anything else. We can compute things, we can simplify and all that stuff. So we're going to take this 3 over n and distribute it in. And that will give us the sum from k equals 1 to n. That hasn't gone away, just like with limits, you know. And then you're going to get 27k squared over n cubed plus 6 over n. So the reason, keep in mind what the problem statement was saying is write a formula for the nth general, the general nth right-hand Riemann sum. So we don't want any summations. And the reason why this is useful now is we actually have a way to do that. The 27 and the n's, they don't matter. The 6 in the n, the 27 and the n cubed, those things are just constants. So n does not depend upon k. N can be moved out front. So what do I mean by that? So this is the same thing as the sum is equal to 27 over n cubed times the sum from k equals 1 to n of k squared plus the sum from 1 over n times the sum from k equals 1 to n of 6. Now, why did I do that? It's because I have a formula for the sum from k equals 1 to n k squared. And I have a formula for the sum from k equals 1 to n of a constant. The formulas from the previous page will allow us to get rid of the summation step. That's the power of that formula. Instead of having to write down all the, on page, what page was that? Page 178. Instead of having to write down a sum of these things, now I can replace the summation with a finite algebraic entity. So the formulas from the previous page, that'll become 27 over n cubed times 2n cubed plus 3n squared plus n divided by 6 plus 1 over n times 6n. That's just from those formulas. Now, get to it in a second. To save on a little bit of time, you notice that you can cancel a small factor here. You can cancel out a factor of 3 on the left. And on the right, you can cancel out that factor of n. So what this ends up being is that r sub n, the general format, would be 18n cubed plus 27n squared plus 9n divided by 2n cubed plus 6. That is the general formula now. That formula will compute the right-hand Riemann sum for any number of rectangles. The utility there being, instead of like, imagine you're a mathematician back in the 1600s, and you wanted to approximate the area of this shape. For whatever reason, for whatever thing you're doing, but you wanted to find the area of this shape. If you wanted to do 1,000 rectangles, doing it the old, like by summing it up, that'd be having to sum up 1,000 different numbers, which even doing that by today, even with a calculator, that would be tedious. They didn't have calculators. But now we have a formula that can just find it for us because of the important facts that we learned on page 180. We had formulas that could convert any one of those summations into a formula. Now, computing the right-hand Riemann sum for 1,000 subrectangles would only require just plugging in 1,000 4 times. Much easier to deal with. So we wanted to use it to approximate r sub 20. So that would be 18 times 20 cubed plus 27 times 20 squared plus 9 times 20 divided by 2 times 20 cubed plus 6, which is approximately 15.68625. When all is said and done, you will get 15.68625, which I think the actual area probably good too. The actual area is 15. So even with 20 rectangles, it's still off by almost a half of a unit, or a little bit more than half a unit. So even with 20 rectangles. And we're going to skip the next one so we can get started with 4.2 right away. It's the same thing, except we're dealing with the left-hand Riemann sum. If you want to, if you're bored this summer, after classes ended, L sub n equals 32 plus 16 over n minus 8n squared plus 8n over n squared. If you want to have some fun this week, this summer, do that. Otherwise, go do something else. Play some Overwatch. I don't know what kids do these days. Some World of War. Do people still play World of Warcraft? A couple of us, me included. So anyways, wish I knew how to quit it. I've played it since I was a kid. Okay. Anywho, so the main reason why I bring that up is this first question. How did that relate to calculus? How is this calculus? This just seems like geometry. We're adding up rectangles. And the statement is I just find a formula for the general nth right-hand Riemann sum, or the general left, or the general midpoint. So one might ask then, if I really wanted to get as exact of an answer as I could, I just keep adding more and more rectangles. I keep adding more and more and more and more and more. Honestly, like I would be taking a limit. That's why I was in the very beginning of the semester, I was saying that limits are central to everything. And I know it seems stupid. They seem like such an arbitrary concept, but they are at the center of all the concepts in calculus. The definition of the derivative. So derivatives in general, the way that they're found originally is by the limit. And then all the formulas that we learned, those were all based on the limit definition. Then we come into integration. And integration is defined by limits as well. So the definite integral, let f be a function on a closed interval a to b, then the definite integral of f on a comma b is a number. I'll explain this in a second. But it's denoted as this big, long, extended S. Like imagine you wrote an S in Word and you just like in a text box and you just stretched it out really far, like putty. That's what it looks like. So that's what we call the integral symbol. We'll write down the notation down here. But this is saying what this says is the definite integral from a to b of f of x dx, and it's equal to the limit as n approaches infinity of the right-hand Riemann sum or the left-hand Riemann sum or the midpoint. They should all coincide, because if they didn't, then math would break, because it shouldn't matter whether you use the left or the right-hand endpoint or the midpoint at the end of the day. Once we do infinitely many rectangles, there should be no difference. So that is the definite integral. What we will learn in 4.3 is the thing called an indefinite integral, which just does this. No numbers. So if you see numbers like on the top and the bottom, the upper and lower bounds, that is a definite integral. And that is a number. Definite integrals are numbers, whereas an indefinite integral is a function. We'll get to that later. But a definite integral is a finite number. And we say if that limit exists, then the function is integrable, meaning that it does have it does have a finite area. So the notation and jargon, I'm going to kind of color code this. So I'm going to make the symbol of the integral symbol right there in purple. And then A is going to be in red, B is going to be in blue, f of x is going to be in green, and the dx will be in orange. Like that. So that is the notation. Much like with limit notation, there were specific things that we had to know about it. Same thing is true here. So this is what they call the integral sign. It tells us we're going to integrate. We're going to integrate. So when we see that symbol, we know we're going to integrate. And because we see the finite bounds, the a and the b, we know that this is going to compute an area, quote unquote, which we'll talk about in a second, why I said area in quotes. But that is the integral sign. It tells us that we're going to integrate. B is what we call the upper limit. And it tells us where to stop, tells us where the area ends. It tells us our last x value. So if it says the integral from 0 to 5, that means that our right endpoint should be 5. And then, as you might guess then, a is the lower limit. It tells us where we begin. So it tells us where our area starts, what x value our area starts with. Then f of x is what we call the integrand. It tells us the function we're integrating. So that's kind of one of those stupid names, like not stupid names, but like those scientific names. So for example, when you do the division algorithm, do you remember all the names of the things? There's the quotient, there's the divisor, and then there's the dividend. Just the thing that you're dividing is called the dividend. The thing that you're integrating is called the integrand. That's all it is. So it's the function that you're dealing with, and that dx is the interesting part. That is the differential. That's the differentiable of the variable x. Now, this is not going to be super important for us because we're always going to be integrating with respect to, say for a few situations, we're always going to be integrating with respect to x. So it doesn't seem like it'll be very, very important. And so some students will actually forget to write the dx. But I will mark down because it's not correct. It's not a mathematically sound thing to say. If you write this, so don't write this down, this is wrong. If you just write the integral from 1 to 5 of x squared plus 2, and you don't write a dx, you have not written a correct mathematical object. That dx, it tells us a couple things. So tells us which integral, it tells us which variable we're integrating with respect to. It also kind of it also ends up being kind of like a period. It tells us that the sentence is stopped. Like that is the end of our integral. That's what that dx tells us. It says we're done writing our integral. Now let's actually compute it. But the most important thing, especially for later on in our mathematical careers, is that it tells you what variable you're integrating with respect to. Just like we don't write dd blank, we don't write dd blank when we're taking the derivative of f of x, right? We would write ddx to say we are differentiating with respect to x. Same idea. We are integrating with respect to x, because if it was a different variable, then f of x would be seen as a constant in the integral's eyes. So that dx tells us a lot. And especially once we get into Math 283, if you decide to take that, you will have to start doing integrals over what we call double integrals. And so you'd have a function f of x, y, and you would have to either integrate with respect to x first or with respect to y first. In the way I've written it right here on the board, don't write this down because this is 283 stuff. But this, like the way this integral is read, this double integral, is saying you're going to integrate this function with respect to x first, then with respect to y. So it matters that you write it, is what I'm trying to really get at here. That dx is an important aspect of the formula. Just like you don't just write lim, you have to write lim as h approaches 0. Because it's a part of it. It's a whole, like it's part of the whole deal. So the key thing, this is the key thing to take away from this section. By the way, this is key. I might study this for the upcoming quiz. Hint, hint, wink, wink. And I'll give you some examples of it in just a moment. But some important notes about it, besides the notation and the jargon, is that x is just the dummy variable. As long as everything is in terms of the variable, you're fine. So f of x dx, f of z dz, f of capital R dr, it does not matter. The variable of integration does not matter. It's as long as it's consistent. If that's if we wrote the integral, so don't write this down, but if we wrote the integral from a to b of f of capital R dx, then this would just be seen as a constant. That would just be seen as a constant. when you're integrating. So that's the reason why it's important to know your variables of integration versus the variables of your function. The other thing is that what I have written up above, and in case there's any secret mathematicians out there trying to catch me slipping up, that is not the actual definition of the integral. The integral's definition is far more generalized and far more open for interpretation, but this ends up being true so long as we're dealing with nice functions, which we always will be. And it ends up being that they're consistent. The formal definition, if you ever want to know, please feel free to talk to me. But it's a lot more awful. Well, beautiful, honestly, but that's my viewpoint on it. So, anywho, any questions so far on this notation? Like that. So the next theorem says if f has a finite number of jump discontinuities, so it has to be a finite number, infinitely many, problematic, anything more than infinite, problematic, then it is actually integrable, which means that the definite integral does exist. That's just an important fact about integration, is that as long as your function is nice enough, you can integrate it, which is pretty cool. We're not going to be tested upon that fact, and it's not super useful, but suffice it to say, there are functions that do not have antiderivatives. There are functions that are not integrable. It does happen on occasion. But so long as your function is relatively nice, you can integrate it. So let's actually use an example. In example 4.1.7, we found the nth right-hand Riemann sum to be written without a summation. And what we found out was, R sub n was equal to 18n cubed plus 27n squared plus 9n divided by 6. Sorry, not 6, by 2n cubed plus a 6. So we now know the general Riemann sum. So that means that the integral from 0 to 3 of x squared plus 2 dx is equal to the limit as n approaches positive infinity of R sub n, which would then be the limit as n approaches positive infinity of 18n cubed plus 27n squared plus 9n divided by 2n cubed plus 6. And we got to do limits again. I know it's been a while. Let's see here. We finished limits in like week 4, week 5. So it's been 8 weeks or so. It's been a hot minute, but there will be limits on the final exam. I don't know what type of limits, but I guarantee you there's at least going to be one thing on limits on that exam because it's cumulative. So it's good to get some practice with this. I'm going to tell you that the answer should be 15. I'm going to tell you this is going to be 9 plus 6, which is 15. And that is our answer. But why? Six is a constant, and the limit of a constant is just the constant itself. But this piece right here, do you guys remember the rules about limits at infinity? So specifically when you're dealing with limits at infinity, when x is going to, when your variable of limits, so n in this case, when n is going to positive infinity, and you've got a polynomial over a polynomial, you've got a rational function, a rational expression, you just look at the highest degree terms. Everything else doesn't matter. So this is 18n cubed plus 27n squared plus 9n divided by 2n cubed. By that property that we learned in unit 1.4, you can ignore the 27n squared and ignore the 9n. They do not matter. So this is the limit as n approaches positive infinity of 18n cubed divided by 2n cubed. Bless you. The n cubeds cancel. We just have the limit of 9, which is 9. And that's how I got that. So we have to use our limit knowledge. Specifically limits at infinity. That's 1.4 if you need a little bit of a touch up on those ones. And it just so happens that if, as long as you got the calculator I recommended, it has a definite integral button. So you can verify that you got the right answer. I guarantee you if you do, maybe during the break, I can show you guys. Sorry, people watching the recording, it's no way to like put it on the screen. But there is a way to do it on this calculator. So I'll get that up during the break. Yeah. Any questions on that? So now we can find the exact amount of area of a curve that's an arbitrary curve. That's a pretty powerful statement if you think about it. You can now find the area of any shape so long as you can find its Riemann sum. That's pretty nifty. Because very, very few things in life are nice circles and triangles and squares and all that jazz. It's much more likely that it's going to be something not nice like that. So find the integral from 0 to 3 of x cubed minus 4x dx. Now, through magic, else r sub n will equal 84 n to the fourth plus 162 n cubed plus 81 n squared divided by 4 n to the fourth minus 18 n squared plus 18 n divided by n squared. Just through magic, not really magic. It's just if you want to go through and find the general Riemann sum for x cubed minus 4x, be my guest. It ends up being a little tedious, but it's fine. But I'm not going to make you calculate for this course. And you can be very, very, I'm very confident in saying this. You will not be asked to find a general Riemann sum. You may be asked to use a general Riemann sum to find a definite integral. So like being given r sub n, can you find that definite integral? Which we can. So now that we know what the Riemann sum for any n value, the sum or the definite integral from 0 to 3 of x cubed minus 4x dx is equal to the limit as n approaches positive infinity of r sub n's. That's 84 n to the fourth plus 162 n cubed plus 81 n squared divided by 4 n to the fourth minus 18 n squared plus 18 n divided by n squared. Because that is the general Riemann sum for that area. That's that would be adding up n arbitrary rectangles from 0 to 3. And now what we're going to do to actually find the exact area, we're going to take the limit as n goes to infinity to get infinitely many small rectangles so that the area, the overestimation or underestimation does not matter anymore, and find it. So looking at those two things as separate entities, this will become 84 over 4 minus 18 over 1. Does everyone see where that comes from? Take a second to make sure you understand why it's going to be 84 over 4 minus 18 over 1. I skipped a step. I skipped a step about limits. Because this is a limit. Because this is a limit at infinity, this 162 n cubed, yes, it's a big number, but in the grand scheme of things, it's not important. Same thing with the 81 n squared. So those things are just out. So we just have this, the end of the fourths cancel, and we get the limit of a constant of 84 over 4. That's why that's there. Same thing here. And that ends up getting us 9/4 at the end of the day. Is that right? Yeah. It doesn't seem right. 80. Sorry, it's not 84, it's 81. 81. That's the reason why it wasn't working out. 81. I'm sorry about that. '81 minus 81/4 minus 8. So that's how you can use Riemann sums to find area. Any questions on that? So you'll be given, if there is any problem involving Riemannian sums, it'll be giving you an R sub n, and you need to find the area using the limits. Okay, let's take a small break. Let's come back at 10:05 or 10. Let's do 10:07. 10:07. And we'll come back then. People watch recording, do some guided meditation, blah, blah, blah. We're back at it, and we get to talk about the area under the curve discussion. Area under the curve. So this theorem, we're gonna have to take a little bit of it, a while just explaining it. Suppose f of x is greater than or equal to 0, then the definite integral from a to b of f x dx will represent the area of the region enclosed by the graph of the function. So as long as the function is positive, i.e. above the x-axis, then the area, the region that's enclosed is actually the area. The definite integral represents the area. However, if your function is less than 0, meaning that it would be below the x-axis, then the region of the area, the region enclosed by the graph fx, will the area of that will be negative the integral from a to b of fx dx. That negative sign right there is important. So why? Why would that be the case? Why isn't it just always going to be the integral from a to b of fx dx? And that's the reason. For that reason, we have to think about, this actually happens a lot in mathematics. The Pythagorean theorem, right? A squared plus b squared is equal to c squared. Like, just as an aside, don't write this down, but when we get x squared equals 4, mathematically speaking, or like, well, let's say we get a squared equals 4, or c squared equals 4 for the Pythagorean theorem. Let's say we get c squared is equal to 4. The mathematical object that we have here has two solutions. It has c equals plus or minus the square root of 4. So it has plus or minus 2. When we solve the Pythagorean theorem in Math 127, all the time, we ignore the -1. We ignore the -2 version, right? Because we're talking about we're no longer talking about a mathematical object. We're talking about a real world object of a triangle, and triangles can't have negative lengths. In the same fashion, the definite integral by itself is a purely mathematical object that we give meaning to it. So when we think about area, now we have to be careful, because area is not just a mathematical concept, it's a real world concept, and we cannot have negative area. That's not possible. So in the same vein of this kind of concept thing, remember, the definite integral way back here is defined as the limit of the R sub n, so that right-hand Riemann sum. And the way the right-hand Riemann sum works, just as a reminder from over here, the way that they work is that they add up all these rectangles, and the rectangles are figured out by having a uniform width that we calculate by looking at the endpoints, but the heights of each rectangle come from the function. So if my function ends up being below the x-axis for whatever reason, then the heights end up being quote unquote negative. And so we have to counterbalance that. All the heights would be negative in this area. So what we do is we multiply by -1 to counterbalance that. Does that make sense? So when you're below the x-axis, it represents the quote unquote area under the curve, because it's not actually area at that point, because your heights would be negative. So if we want to find area, we're talking about a intrinsically mathematical concept, or like a real world concept. And so we have to take that into account. So we tack on the negative sign to make sure that any piece that's negative becomes positive. And that being said, it all depends on the context. So a definite integral can be positive, it can be negative. That's fine. You can have the, like, for example, the integral, which we'll calculate soon enough. We'll be able to figure this out in 4.4. But the integral from 0 to 1 of 4 dx, negative 4, will be, from 0 to 2, will be -8. The answer for that definite integral will be -8. But if we wanted to know the area of that region, we'd say +8. So it all depends on the terminology being present. It is okay for a definite integral to be negative. That is fine. What is not okay is for an area to be negative, because area is not just a mathematical concept, it's a real world concept, which means it cannot be negative. You don't have negative area yet. Maybe someone later on will figure it out. So notice the terminology of this problem. Use the definite integrals to represent the area of the shaded region. So if I'm asking you to find area, we need to tack on the negative signs as necessary. But if it's just saying find the definite integral, could be positive or negative, doesn't matter. But this one, this is the curve e to the x on the interval 1 to 2. So this is above the x-axis, so the area of that region will be the integral from 1 to 2 of e to the x dx. That's it. And you can compute it if you want to by using your calculator. You should get, at the end of the day, it'll be e squared minus e. That'll be the area of that region. But we'll get to that soon enough. The second one, though, notice that the curve is below the x-axis. On bracket 0 to 4. So the area of this region, if I wanted to know the actual area, I would tack on a negative sign to counterbalance it. So the integral from 0 to 4 of the square root of x minus 2 dx. And that's the area. Last but not least, we have this region here shaded from sine of x. Now notice, what's this value here? Does anybody know? Should know. Pi and 2 pi. So there's two separate regions. One region is above the x-axis and one region is below. So I'm going to need to calculate the area of those two regions separately. R sub 1 and R sub 2. Total area, so A sub total would equal area of R sub 1 plus the area of R sub 2. The area of R sub 1, it's above the x-axis. So the definite integral and the area coincide. So that will be the integral from 0 to pi of sine of x dx plus negative the integral from pi to 2 pi of sine of x dx. Because fun fact, if you did, and you could do this on your own time, the reason why I couldn't do this as one singular integral is because one piece is above and one piece is below. If you do the integral from 0 to 2 pi, instead of just 0 to pi and then from pi to 2 pi, you will get the answer will be 0, because all that positive area from the first piece, it's symmetric across this line. It's anti-symmetric across this line. So this bit of area gets counteracted by this bit of area. This bit of area in the middle gets counteracted by this area, and they kind of cancel each other out and get 0. So if you want to sometime find the definite integral of sine of x from 0 to 2 pi, you'll find that the actual definite integral ends up being 0 there. But the area ends up being 2? 4. Yes, 4. All right. Any questions on that? All right, so use definite integrals to find the area of this region. Now, I know it's pretty clear from the drawing that I drew where the intersection points are, where it goes from being positive to negative, but let's just assume that we didn't have that. So first, need to find these x values. Because at those two x values, that's where the curve will switch from being positive to negative or negative to positive. So yes, they are 2 and -2. Yes, I know, I see it. We all see it. It's there. But what if this wasn't given? What if the tick marks were not given? You had to find it out. How would you find out where it crossed the x-axis? Take a second to think about that in case you don't already know. It crosses the x-axis. That would be a place where its y-coordinate would be 0. So you want to find out where the curve equals 0. So x squared, negative x squared plus 4 equals 0. That gives me x squared equals 4, which gives me x equals 2 and -2. So we'll call this region 1, region 2, and region 3. So the area total would be negative the integral from -3 to -2 of negative x squared plus 4 dx, plus the integral from -2 to 2 of negative x squared plus 4 dx, minus, or plus a negative, doesn't matter how you want to write it, from 2 to 3 of negative x squared plus 4 dx. The first and the third are the areas of the regions 1 and 3. The middle one is the region 2, and that one's the only one that's positive because that's the only piece that's above the x-axis. Any questions on that? I put this next problem on the exam, or not on the exam, on the notes, because this problem actually ended up costing me 10 points on my exam when I was taking Calc 2. Because the only way to compute that by hand, so we will learn ways to compute these things by hand instead of having to look at them as purely math, like using our calculator. But in order to do that calculation, in order to find the antiderivative, to find the square root 4 minus x squared, in order to find that, you have to know a thing called trigonometric substitution, which we hadn't learned yet. So we had to think about this outside the box. That's what the teacher was going for. But I didn't get it. So I ended up getting a 0 on that problem. And so you guys got to experience it like I did. But in a much more structured format that's safer, instead of being 10 points on a 50-point exam. Not better. So the fact of the matter is, we're going to use geometry. That was the solution. That was the way to figure this problem out. I just didn't think about it. So the integral from 0 to 2 of the square root of 4 minus x squared. Does anybody know what the curve y equals the square root of 4 minus x squared is? It's an upper half of a circle, because if you square it, both sides, you'll get x squared plus y squared equals 4. Circle, but we're talking about the positive square root, so it's the upper half. So you're looking at it, you're looking at this picture. Does not need to be perfect. But here is 2, 2, and then -2. And so this is that curve. But we're talking about the integral from 0 to 2. So we want this region in question. A sub r is equal to the integral from 0 to 2 of the square root of 4 minus x squared. And that's a quarter circle. With radius 2. So because it's a quarter circle, the area of a full circle is pi r squared. So the area of a quarter circle would be 1/4 pi r squared. 1/4 pi r squared, but in this case, that'd be 1/4 times pi, or 1/4 pi times 2 squared, which just ends up being pi. The area of that region. So all I need to do on my exam is I just needed to write pi, and I would have gotten 10 points. Frantically tried everything I could think of, except for the one thing that was standing right in front of me. The fact that we can also think about definite integrals as purely an area. A definite integral is an area, like quote unquote under the curve. Because if it's below the x-axis, then it's negative and so on and so forth. So next one, I wouldn't expect you to know this offhand, but absolute value of x, that's the V shape, but it's negative absolute value of x, so it's going to be reflected across the x-axis. And then it's got a +1 on it, so it's shifted up 1 unit. This curve looks like this. Here's 1, here's 1, here's -1, and the curve looks like this. That's y equals 1 minus the absolute value of x. And we're talking about the region right here. That's the area, that area is a triangle with height 1 and base 2. So the area of this region would be 1/2 the base times the height, which would be 1/2 the base 2 times the height 1 is just 1. The area of that region is 1 unit squared. And if we're finding definite areas and areas of arbitrary mathematical concepts, you don't need to write units squared. I'm not going to be that particular. Technically speaking, it should say units squared, but all right. Any questions on those? Okay. So now we get to write some properties about definite integrals. Some very, very fun ones, honestly. These are really cool processes. I find that the integral is definitely one of the most fun things to work with. It has a lot of cool properties that allow you to do some fun conceptual problems. So first and foremost, suppose k is any constant and the following integrals exist. Just make sure that this thing all works out. The integral from a to a of fx dx is 0. Why? Yes, exactly right. If we're integrating from a to a, that means we're trying to find the area of the region under the curve f at a singular point. There's no area. It's a one-dimensional object at that point. Like if you're looking at this, let's just say this is the curve for a second. Here's a. If I want to find the integral from a to a, I'm looking at a vertical line, and the line has no area. Like, yes, I've drawn it, and it looks like it has area, but that's because it's a line. It's drawn with a pencil. An actual line doesn't have any area. That's the reason why the area, the definite integral from a to a of fx dx is equal to 0, because you're not integrating anything at that point. The integral from a to b, and I'm going to color code this, a to b, green, is equal to negative the integral from b to a of f of x dx. which seems weird, understandably so. The integral from a to b is equal to the integral from b to a times the negative sign. So like it's basically, if you're going to integrate backwards, you have to take on an extra negative sign to counteract the fact that you did it negatively, you did it backwards. That's what that does. Very, very niche situation where that's useful, and we'll see this in a second. But that is an important fact, is that the integral from a to b of f(x) dx is equal to negative the integral from b to a. So if you change the bounds, you have to tack on a negative sign if you do want to change those bounds. Next one makes a lot of sense. The integral from a to b of k f of x dx is equal to k times the integral from a to b of f of x dx. Now, why would that be true? So I'm going to check, make sure we got that problem, and that problem. Okay. Now, the reason why that's true, we would hope it to be true, right? We would, like, just like with limits and derivatives, that constants don't matter. But if you think about it geometrically, what is the difference between f of x, sorry, y equals f of x versus y equals 2f of x? If you remember your linear transformations, just a smidgen, basically 2f of x vertically stretches the graph by a factor of 2. Essentially, it takes all of your y values and doubles them. So here would be f of x, and let's just say this is 1, then here is 2, and here is the curve y equals 2f of x. It doubles everything. So essentially what you're going to do is you're doubling the area that's present. Right? Like, it's not exactly this, but basically what's happening is you're going to multiply by 2 to find the area of 2f of x. So you can just bring the constant out front, is what's going on there. So constants can be ignored just like normal, just like with everything else we've dealt with. The integral of f of x plus g of x, plus or minus rather, is equal to the integral from a to b of f of x dx, plus or minus the integral from a to b of g of x dx. Meaning that we can combine, we can separate, and then remember, this is an equal sign, so it works forwards and backwards in terms of its implications. Means that not only can you separate integral, but you can combine integrals so long as they have the same bounds. Notice that if you want to combine them, they have to be both starting at A and ending at B. If they start and or end at different numbers, you cannot combine them because you're not talking about the same piece. Yes. Yes, exactly right. So if you want to combine them, if you want to go backwards, if you want to go this direction, they need to have the exact same bounds. Otherwise, you cannot combine them. And last but not, or second to last, or fourth from last, excuse me. The integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx for any c value, regardless of size. So what do I mean by that? What I mean is you can have, so you don't need to write this down, but the integral from 1 to negative 1,000 f of x dx plus the integral from negative 1,000 to 16 f of x dx. This is the integral from 1 to 16 of f of x dx. So it doesn't matter. The c value can be in between a and b. It can be above both of them. It can be below both of them. It can be a fraction. It can be anything we want. But as long as they, like, the first one starts with the or ends with the number that the second one starts with, you can combine the two of them. It's a very, very nifty trick. And then once again, so it works for anything. That's really nifty about it. And the key thing to remember, something that students always tend to forget, and I understand why. An equality sign means that it's true backwards and forwards. So what this tells us additionally is that you can split up any integral into pieces. And that makes sense, right? If I have if you're looking at a graph, here is 1, here's 5, and here's 3. If this is my curve, this would be the integral from 1 to 3 of fx dx. And then this would be the integral from 3 to 5 of fx dx. It kind of makes sense, right? If I wanted to find the integral from 1 to 5, I would just add up these two pieces. So this part E is kind of one of the most useful aspects of the definite integral. In fact, you can split apart an integral into pieces if you go backwards, or you can combine different pieces if you go forwards, in terms of the implications of the equal sign. The next one is that if f of x is greater than or equal to 0 on the interval a to b, then the antiderivative, or the definite integral from a to b of fx dx is also greater than or equal to 0. And that makes sense. If your function is above the x-axis, then you're going to be adding up positive area. That one is used in the proof of G and H. Which says that if your function is smaller than another function, then the antiderivative, or the definite integral of a to b of f of x dx is less than or equal to the integral from a to b of g of x dx. Which kind of makes sense. If your secondary function has a larger height for all of its rectangles, you're going to be making a bigger area. All of these facts can be deduced simply by thinking about these things as geometric objects. That's what I love about this thing. Save for, I'd say, part B and then and H are ones that don't really that don't follow geometrically per se, but it's all just looking at blocks, looking at different size blocks. And the last one says that if f is sandwiched, so if f is bounded above and below by a lowercase m and a capital M respectively, then that would mean that the integral from a to b of lowercase m dx is less than or equal to the integral from a to b of f of x dx, which is less than or equal to the integral from a to b of capital M dx, which ends up being the more important version of this is m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to capital M times b minus a. Now, I'm not going to test you on this one, though. This is just for the proof of the fundamental, this is useful for proof of fundamental theorem. In section 4.4. It's useful to the proof of the fundamental theorem of calculus, which we'll get to soon enough. We got time. We got time until we get there. But if you're wondering how does the integral from a to b of m dx equal m times b minus a, that's a good question. You can think about it geometrically to understand that. You don't need to draw this, but just observe. What I'm saying, just in visuals, here's lowercase m, here's capital M, and here's f. Right? So if f is sandwiched between, the area of f would be larger than the area of m and smaller than the area of capital M. That's the implication. But now, why does it become m times b minus a? It's a great question, and I'm glad you asked it, Justin. Glad you asked that question. So here's A, here's B. We're talking about the area of this shape right here. That's a rectangle, right? What's the height of that rectangle? M. And what's the width? A to B, which the distance is B minus A. So this is just the area of a rectangle with height M, and this is the area of the rectangle with height capital M. That's the reason why the formula is the way it is. So either way, now we get to the fun stuff. These are the conceptual questions that I absolutely love. Start off small, and then we'll work our way up. So let f and g be functions such that the indefinite integral, or the definite integral from 0 to 5 of x dx is 10, from 5 to 7 is 3, and 0 to 5 of g of x is equal to 2. Find the integral from 0 to 7. So what I like to do to figure these things out, I think these things are fascinating. And what I do is I just imagine over here, I'm going to draw a line and say, this is the curve f of x. And here's 0, here's 7, and here's 5. I know this is this piece. And I know that this is this piece. So I just draw that to visualize this to myself. I want to find the integral from 0 to 7. So how do I find it? So add them up, because I have the first piece in red and the second piece in green. Add those two things together, I get the whole thing. So I split this integral up into the integral from 0 to 5 of f of x dx plus the integral from 5 to 7 of f of x dx. So that's 10 plus 3, that's 13. So this picture that I drew, that helps me visualize it, but it might not help you. If it doesn't, no big deal. If it does, awesome. I find it like this one, not too hard to see that. The next one, you'll see why I do it more often. The integral from 5 to 0. And from 5 to 0, that's just the reverse way. We have the integral from 0 to 5, so this is just negative the integral from 0 to 5 of f of x dx. So that'll be negative 10. Any questions on that? All right. Integral from 5 to 7 of 2f of x dx. By the rules of integrals, constants do not matter. They can be brought out front. So this is really the 2 times the integral from 5 to 7 of f of x dx. And we know what that integral is. We already have it. It was given to us in the problem statement. It is equal to 3. So this is equal to 2 times 3, which is 6. And last but not least, the integral from 0 to 5 of f of x minus 4g of x dx. So using all the properties we know about integrals, you can split this up into the integral from 0 to 5 of f of x dx minus 4 times the integral from 0 to 5 of g of x dx. 0 to 5 f, that's going to be 10. The integral from 0 to 5 of g of x was 2, so that's 2 times 4 times 2. That's going to be a total of 2 at the end of the day. Boom. Any questions on that? Also, I realized I kind of skipped over something real quick here. don't need to write this down, but if you're wondering, why is that the notation for the definite integral? Why did we write it that way? So what I told you was that what we have is that the integral, so we're the limit as n approaches positive infinity of r sub n, which would be the limit as n approaches positive infinity of the sum from k equals 1 to n of f of a plus delta x times k times delta x. So the reason the notation is the way it is, the reason what it is, this is an infinite sum. What is the letter, what is good practice problem for my son? What does sum start with? It starts with an S, right? So if I took an S, it's a really badly drawn S. And what if I just grabbed that and I just, oh, darn it, it won't let me. You can see what I do. Like I stretch it with putty, and then eventually it would look like this. It would look like this for sum. So the integral symbol is basically just an elongated S to represent sum. And then dx, if you remember what we called that an infinitesimal. It's an infinitely small change in x. So delta x, by definition, is b minus a over n. And as n goes to infinity, that distance gets smaller and smaller and smaller and smaller until it's basically 0. So it's an infinitely small change in x. That's why the delta x now becomes a dx. And then just the function is in the middle. That's the reason for the formula, why it's written the way it is, if you're curious. That's the reason why we have it written the way it is. So, okay. Let's do this last one. Well, there's 2 more to do. 4.2.8 is really fun, but we'll get to it. This one. So this is all, there's no g, there's just a function h. We know it's integral from -3 to 4. We know it's integral from 0 to 4, and we know it's integral from 0 to 6. So the way I like to write this is I draw a number line. I write all my points. So -3, 0, 4, and 6. And I just draw this generic curve. There's a lot of different ways you can draw it. Here's f. I know this first one, so I know the integral from -3 to 4. I also know from 0 to 4. And I know from 0 to 6. I know all those pieces. So how would I find the antiderivative, the definite integral from -3 to 0 of h of t dt? Don't answer. Let everyone get a chance to think about it based on our picture. What do I want? I want this piece right here from 0, -3 to 0. How would I find that? Yes, so taking the red and taking off the green from it. If I take the big red and subtract off the green, I'm left with the orange. So this is equal to the integral from -3 to 4 of h of t dt minus the integral from 0 to 4 of h of t dt. Taking the bigger area and subtracting off that little tiny piece. And we already know what those numbers are. The first one is 5 minus the second one, which was 2. So the total area is 3. Now, this next one, we already just found in part A, we found out what 0 to 3 is. We already found out what that answer was. So from part A, we know what the integral from -3 to 0 is. It's 3. So this will be 2 minus 3. So the area of the answer for that is -1. So we couldn't do B unless we found A first. Any questions on that? All right, now I want you to try and figure out number, part C, the antiderivative, or keep saying antiderivative, sorry. The definite integral from 4 to 6 of h of t dt. What would that be? Take a second. You can draw it each time if you want to. Sometimes I do that. I draw a new one each time, but I'm just going to stick to this one though right now. What would it be? You take the pink area, that's from 4 to 6, from 0 to 4 to 6, and subtract off the green area from 0 to 4. That would get you just the area from 4 to 6. So this is going to equal the pink minus the green. So that's going to be the area from 0 to 6 of h of t dt minus the area, or the indefinite integral from 0 to 4 of h of t dt. Both the things are given. That's going to be -3 minus 2. That's -5. Any questions on that? Fun geometric puzzle, right? At least I think so. I think these are nice, fun geometric puzzles. And the last one here, the integral from -3 to 6. That's the whole kit and caboodle. So there's a lot of different ways we could figure it out. We could do the integral from -3 to 4 plus the integral from 0 to 6, and then subtract the integral from 0 to 4 because we're doubling up on that area. That would be one way to do it. We already found in part A, we found the integral from -3 to 0. So we could just add up the part A with the pink. That would be one other way. There are so many ways we could do this. That's the cool thing. We also, just in part C, we found the integral from 4 to 6. So we could do the red plus the 4 to 6. They should all give us the same number. Does that make sense? Does anybody need me to say that again? So there's a lot of different ways. Lots of ways. So I'm going to do the integral from -3 to 4 of h of t dt plus the integral from 4 to 6 of h of t dt, which was found in part C. So that would be 5 plus -5, which is 0. Once again, it is okay for an indefinite integral to be negative. It is okay, sorry, it is okay for a definite integral to be positive or negative. Area, though, area cannot be negative. Area has to be positive. So that's where we'll leave it for today. We'll finish up that last one tomorrow or on Wednesday. Quiz on Wednesday is just on the 4.2 that we've gone over so far. So nothing on 4.1. No summations, no nothing like that. The only thing that would be on there would be like given a right-hand Riemann sum or representing area with integrals. Okay, that'll be it for today. I'll see you guys on Wednesday. If you have any questions, feel free to ask. Because it's on Wednesday, just 4.2.